Hello, everyone. So I'm Arif BADROU. I'm a third PhD student. So I'm very glad to be here and to present my works on the development of a numerical tool to assist endovascular navigation by active multi-curve catheterization. So it's a work conducted at the LaMCoS laboratory at INSA de Lyon. And this project gathers both academic and industrial partners and is funded partially by the National Research Agency. So just a few words about the context. So the project is called DEEP project, and the goal of the project is to facilitate endovascular navigation to complex targets. An example of complex targets and what interests us here is the navigation to the brain through the left common carotid artery. Among the endovascular therapies, 20% of them present this kind of difficulties, leading to navigation failure. The DEEP project intends to overcome these difficulties with the use of innovative surgical tools and decision support tools. For example, in your case, the French Society based Vascular developed an active guide wire made of shape memory allow. So this device is capable of bending in a multi-curve way, drawing a kind of A shape, as you can see here, facilitating the hooking of the left carotid common artery. So I just introduced you the context. Now I will present the model and its use and some results about numerical charts. We just developed a finite elements model to represent the navigation in a phantom aorta of the active guide wires and catheter from the market. So the phantom aorta contains one block here, as you can see. The box contains an aortic kind of patient-specific aortic shape, which can be changed with another. And our model, as you will see in a moment, is able to reproduce passive navigation, as you can see just here, and activation of distal moduli, the two distal moduli I just mentioned before, and a particular effect which is called snapping. So just to explain in few words what is snapping. So when the active guide wire is in contact with the aortic wall and you activate the distal moduli, there is a kind of rotation, a buckling in rotation of the active guide wire, tending to stabilize the device and pointing it in an opposite way. So our model was validated in two ways. So against active sequences. So here we took into consideration 4 key moments. So in 1 and 2, it's just passive navigation to reach the left carotid, to be near the left carotid, as you can see here. And in 3, we activate the distal moduli, and in 4, the snapping occurs. So in the chart just here, we follow the tip coordinates of the end of the active guide wires, and we see the comparison between experimental and numerical navigation. So we also validate our model against passive sequences. At the top level, we have the simulation, and just below, we have the navigation through the phantom aorta. Our aim was to respect the behavior of the tools, respect the interaction between the active guide wire and the aortic wall, and between the tools themselves. Okay, so now our model is ready and validated. How could it be used? There are 2 things. The first thing is we can help with the design of the active guide wire. For example, here, and I present my model, but by the way, we have the active guide wire and we have the catheters and the rigid phantom aorta. We change the design, the distal moduli, in order to hook the left carotid, proving that the navigation, the success of navigation is partially driven by these parameters. And another way to help to develop tools is to help the clinician with decision support tools. All of this using HOPGD, which is a reduced order modeling method. So here is the first example to help the clinician with an example of decision support tools. So if we fix the aorta, taking, for example, this one, kind of standard aorta, I need 3 hours to simulate something like this with finite element method. So if I change my parameters, if I change the design of the active guide wire, if I change the navigation parameters, I need to wait 3 hours more and so on. So the idea is to create a numerical abacus giving the response in real time. So for example, I took 2 parameters. The 2 parameters are related to the time during which I push and I pull my active guide wire. Here I push my device, and just briefly we'll see that I will pull it. Just stabilize it. The first thing I need to do to use HOPGD method is to feed my algorithm, and to do so I need to make some pre-computed snapshots evenly distributed in the space parameter. So here, for example, I took 3 values per parameter. So here in my 9 snapshots. And for a new set of parameters, the new value will be interpolated in the space parameter. So here is an example of my abacus. So you have my 2 parameters. So I fixed, for example, 5.1 for the first one and 12.4 for the second parameters. And you can see in real time, during time, you can see directly the response of the tip of the active guide wire. So I just need to adjust my parameters in order to see which ones can lead to the hooking of the left carotid. Another example is for the design of the active guide wire. So here is my guide wire with a little length of the shaft. I have, in this case, 5 parameters. The distal length, distal moduli length, just here, LP and LD, and the gap between them. And the 2 last parameters, as you will see here in percent, are related to bending performance. 29 is considered as low, and 100 is the maximum power of my device. So here again, it is slightly different because one snapshot takes me about 2 or 3 minutes. So here again, if I change my parameters, there is no big change because the bending performance are very low. But if I put it at 100%, I can change directly. I can have a response in real time. Okay, so what could be the perspective of this project? In fact, we want to create numerical abacus with more control parameters. We talked about 7 parameters, but for different typical anatomy. So we started by classifying our anatomy by taking some criteria, and we want to have dedicated abacus to each type of anatomy. For example, here we have a standard aorta. Here you have a bovine aorta. Here you have a more complex aorta. So it's just an example, and it's why we want to go on. So thank you for your attention. If you have any question,